In week 3, we're going to start chapter 7 today, dislocations and strengthening mechanisms. We're going to be taking a step back from the macro scale, kind of, just for a little bit, and we're going to go back into the atomic scale to see kind of why deformation occurs in materials, metals more specifically, but we'll be touching on each material type. And then also, we have the little caterpillar analogy for dislocation motion. We're going to talk about that as well. Okay, lesson objectives for today. We're going to describe edge and screw dislocation motion from an atomic perspective. We're going to describe how plastic deformation occurs by the motion of edge and screw dislocation in response to applied shear stresses. We're going to define slip system and cite an example of a slip system. We're going to calculate the yield strength of a single crystal under a tensile load. Describe how the grain structure of a polycrystalline material is altered and when it is plastically deformed. And we're going to explain how grain boundaries impede dislocation motion and why a metal having small grains is stronger than one having large grains. Okay, so here's edge dislocation motion. So when we start to plastically deform a material, we're starting to break bonds, certain bonds in that material. And instead of like completely breaking away, what will end up happening is, before we get to that point, we're going to have our dislocations begin to move around inside of the crystal lattice. So if we look at this edge dislocation right here, so we've got our edge dislocation line, and we apply a shear stress to this material. So we've got some shear going this way and some shear going that way. This edge dislocation is going to want to move. Okay, it's going to, these bonds right here are going to break and then reconnect to these. And that's because, remember, metal atoms, they typically don't care what atoms they're connected to as long as they're connected to other atoms. So if there's enough force acting on this, these bonds will break and reconnect to and fill this gap, essentially. What this does is it has the effect of essentially causing just a very small motion of this half plane of atoms over to this side. So these atoms will now become the half plane of atoms, right? And you can think about it as the half plane of atoms moving. That's not really technically correct, but the dislocation is actually the thing that's moving, okay? Now what happens is if this happens all the way throughout the body of a material or a grain, what will happen is that half plane of atoms will move all the way out to the far edge. And now we have an extra half plane of atoms that is literally on the very edge of the material, and so that edge dislocation has now essentially disappeared because it has moved all the way out to that outer edge. Okay. So again, here's the caterpillar analogy. So it's a lot like a caterpillar when it inches its way along like a surface. It has a little hump that forms, and this hump moves as the caterpillar moves. And because each of its two little legs move over one step when this happens, it has the effect of moving the entire caterpillar over one set of legs in that direction, if that makes sense. And so that's what's happening here. Again, here's that same kind of analogy, just with a little bit more of a basic like aesthetic, but we have our half plane of atoms here. If we move this half plane of atoms using shear stress all the way to the far edge, we get this. And what you can see what this kind of looks like, it looks like the material has now plastically deformed in a certain direction. So again, here's our analogy for, or our visual for edge dislocation. And then if we move into screw dislocations, remember we talked about both edge and screw dislocations. And then also mixed dislocations, but they're just a combination of edge and screw. The same thing can happen with screw dislocations. So we apply a shear stress in the same way, or a similar way, but instead of moving the entire half block or instead of moving the entire two halves of the surface along one another, this actually unzips. So instead of moving kind of like this, we're moving kind of like that. And it ends up having the same effect when that unzipping falls to the very edge of the material. And so we will get something that looks similar, actually. Okay, so again, here's just an image of our metal atoms with our electron cloud. And again, if this set of metal atoms, let's say this one on the very top, decided to move over one step, these other metal atoms wouldn't care, right? Because to these metal atoms, each of these other metal atoms are the same exact thing, and they don't mind at all if there's a little bit of a motion here. Of course, it does take some force to do this. It's not going to happen by itself. But if you do apply enough of a force, you can persuade these metal atoms to break their connections with the atoms that they're bonded to and to move over one step. Right? And of course, with actual macro scale deformation, when I say one step, that could end up being like millions or billions of steps if you think about how many atoms are inside of a material, right? Okay. So for metals like copper, aluminum ion, this dislocation motion is relatively easy. And metallic bonding is non-directional, okay? It's non-directional, so there's no problem with this. And so we have close packed planes and directions for slip. Now we're going to change things up a little bit. We're going to look at covalent bonds and ionic bonds. Now, covalent bonds do not want to slip. They do not want to slip. Because remember, the covalent bonds are sharing electrons between atoms. And so they are connected to those atoms, and they don't want to move. So this actually means that our dislocation motion is relatively difficult because we've got really strong bonds holding these together. That covalent bonding is also directional. So because it's directional, having just one set of atoms on one side versus the other, because it's not non-directional bonds, that's going to affect how easy it can slip. And so those two things combine together to make covalent bonds or covalently bonded materials really difficult to deform. And so if you think about things that will shatter when they break, if it's not an amorphous substance, if it does have a crystal structure that we can identify, it's probably because it's covalently bonded. You also have ionically bonded ceramics, and these are a little bit between the two. So these are relatively non-directional, but there is a caveat to that in that you have positively and negatively charged ions, and the negatively charged ions want to be in full contact with other positively charged ions, okay? So it wants to maintain this structure all around the negatively charged ions. So what this means is that this is relatively difficult dislocation motion, but if you can get this to slip over two atoms instead of just one, like for example in metallic bonds, you can slip on one plane or one atom at a time. These will have to slip two atoms at a time, and so it makes it more difficult. And so there are very few slip systems for this kind of thing. And the motion of nearby ions of like charge is restricted by the electrostatic repulsive forces. Okay, so let's talk about slip systems. Let's just cross that out. All right. Slip systems involve a combination of slip planes and direction, okay? So we're going to have a slip plane and a direction. All right. So what are those? First, we have the slip plane. And this is a crystallographic plane Okay, now we know a little bit about crystallographic planes, right? Because we've learned actually how to calculate the Miller indices of a crystallographic plane. But it's a crystallographic plane on which slip occurs more easily. Or most easily. We could say most easily. Okay. And usually this always occurs on planes that have a high planar density. And remember, we have discussed how to calculate planar density as well. So you can see we're not covering things you don't need to know. Everything's connected. Okay, so planes that have a high planar density. All right, now we need to have our slip direction. And this is the crystallographic direction. Along which the R slip occurs. And then as a little added bit, along which slip occurs most easily. So which direction is it going to want to slip in? And what is that plane that it's going to want to slip along? And this direction should also have a high linear density as opposed to planar density. Okay. So there's our slip systems. So here's an example of a slip system. This is the FCC crystal structure. And we're looking at the 111 plane, okay, in the 110 direction. Okay, so here is our direction. It's not this black arrow, it's this pink arrow, right? And that is the direction along which this is going to want to slip. You'll notice, though, that there's multiple pink arrows here because they could slip in any of these directions, okay? So you might have slip occurring in any of these based on how that shear stress is applied to the system. And for the FCC unit cell, we have a total of 12 independent slip systems that are possible, okay? You could slip along the top plane or the bottom plane, look at the planar density there, or you could slip along this diagonal plane, the 111 plane, for example. And so you can just look at how many different planes are possible, and you can see that there are a bunch of options here for the material to slip. And then for BCC and HCP unit cells, we have other slip systems that are possible, right? Maybe not the same directions, but whichever has the highest planar density, whatever planes have the highest planar density, that would be the most likely place for it to start slipping. Okay, so when we look at single crystals, we can actually identify like our slip planes, like after fracture. So remember the aluminum test strip that we were looking at last lesson. It wanted to slip along a certain diagonal. There are other reasons why this happened as well, but there is a convenient slip direction associated with that also has a hand in making it neck and break in that specific direction or orientation. So applied tensile stress, the shear stress component when slip plane is oriented neither perpendicular nor parallel to the stress direction. So our stress direction is along this axial direction, okay? And our applied tensile stress is the tensile stress that's occurring normal to the slip plane, okay? And so we have our F prime, okay, acting normal to our slip plane, and then we have A prime. A prime is actually the area of this diagonal, okay? So we have our typical area, but it's not. This is our A prime is going to be larger because it wants to slip along this plane, and therefore we need to take the orientation of that plane into account when looking at our area. So that is our applied tensile stress or resolved shear stress, I should say. That is how you calculate our resolved shear stress. And then our resolved shear stress depends on the orientation of the normal to the slip plane and the slip direction with direction of tensile force F. Okay, I've already explained that. And then F prime is equal to F times cosine, or our regular force multiplied by the cosine of lambda. And lambda is that angle between our axis and the slip plane. Note that it is actually in the acute direction. The more obtuse angle is not used for this calculation. It's the one that is closest to the axis, if that makes sense. The shorter angle, basically. And then A prime is equal to the typical, it's equivalent to the typical area divided by cosine of theta, or phi in this case. And that is, again, that measured angle along the axis relative to our slip direction. And that slip, it's actually normal to the slip plane. So this arrow is pointing straight out of that circle, okay? So if you put this arrow, the tail of that arrow in the dead center, and then it is perpendicular to that plane, so it's pointing straight out, it is that angle from that vector that is normal to the slip plane to the axis. Okay, and so we have a relationship that's between our tensile stress and our resolved shear stress. Okay, so remember, we can calculate tensile stress really easily. It's just force over area, right? And resolved shear stress is related to it. So resolved shear stress is equal to force over area, which is our stress, cosine lambda cosine phi. Okay, so resolved shear stress is equal to stress multiplied by cosine lambda multiplied by cosine phi. Okay, so now we're going to talk about critical resolved shear stress. Okay, critical resolved shear stress. Basically, there's a critical value of shear stress that can occur, or resolved shear stress that can occur along the slip plane that that will be the point at which slip will begin to occur. Okay, so when we were talking about critical resolved shear stress, it's a lot like you could think of yield stress, for example, but it's in this specific scenario, and it's a shear stress that we're talking about here. So it's usually between 0.1 to 10 megapascals is where our critical resolved shear stress lies. And in a single crystal, there are multiple slip systems and a variety of orientations. Okay, so you kind of have to keep that in mind. We're just showing one in this picture right here, but there could be many that could be active, right? In fact, in that video that I showed you of the tensile strip, it was breaking along a slip direction, and then another one was forming at the same time. So it had actually passed the critical resolved shear stress in two different slip planes. Okay, it just happened to break first along one of them, because maybe that shear stress in that direction was a little bit higher, or maybe there were more defects in that direction, that kind of thing. There are a lot of reasons why it might break on one slip plane as opposed to another. So let's see. And then the yield strength of a single crystal. Okay, so I had already used our critical resolved shear stress as like an analogy for yield stress, But as it turns out, they are related, which makes sense. So our yield stress for the single crystal material, which we're not going to encounter very often, is our critical resolved shear stress divided by cosine lambda cosine phi again, max. Okay, and that would be the maximum of these two. And something to note that's a little bit important about that is, why are we saying max here? Well, it's because we might have multiple slip planes that we're looking at, right? So we're looking at the slip plane that gives us the maximum cosine lambda cosine phi, okay? That will usually be the slip plane it'll want to start breaking along. Okay, so on the macroscopic scale, of course, we have multiple slip planes that can occur. Even the same slip plane can occur in multiple places, right? So you can have parallel slip steps that form on the surface of a single crystal. In fact, this happens all the time. The steps result from motion of large numbers of dislocations. I mean, hundreds of thousands, if not, millions of dislocations that are present in the material that are on the same slip plane. And sometimes on single crystals, these appear as slip lines. And we're going to show you some slip lines here in this next slide. So here are, for this material that's been put through a certain amount of stress, you can actually see these slip lines generated on the surface of these crystals. Okay, this is actually a polycrystalline material, so you can see these grain boundaries here, right? But you can see these slip lines are being generated. And you'll notice that for this polycrystalline material, these slip lines are actually in different directions, right? Because the grains are oriented in different directions. So those slip planes are now not unified with one another. And so on the application of stress, the slip plane, or the slip in each grain, happens along the most favorable slip system relative to our stress. And so it'll have the largest resolved shear stress, and it'll only happen when our resolved shear stress goes over our critical resolved shear stress. And so yeah, and you can see these different orientations. Okay. There's also something else that's interesting that happens here. So when you work with a material and you deform it, you can actually change the grain shape. So the grains change shape and become distorted during plastic deformation because of slip. And the manner of grain distortion is similar to gross plastic deformation. Okay, what do we mean by gross plastic deformation? Well, if I look at this piece of material before rolling, what we see is a bunch of small crystals that are relatively similar in size, that are called equiaxed. And then after rolling, they become misshapen and oblong, and now they're columnar, or more columnar than they were before. And that's what we call gross plastic deformation. It looks like we just took it and stretched it, right? So before rolling, grains are equiaxed and randomly oriented, so they have isotropic properties. But after we roll it, the grains are now elongated in the rolling direction. And this causes anisotropy, right? And it rolls along the preferred crystallographic orientation of the grains, okay? Now, what do I mean by rolling? Well, this is a specific manufacturing process where you take a sheet of metal and you literally put it through these big, heavy rollers, and it flattens it into a much smaller shape, much thinner, right? And that's what you get, okay? So there are things that we can do at the macro level that actually directly affect things that are happening in the crystal structure. We can actually adjust the crystal structure to suit our needs in certain ways. And we're going to talk about that. So how can we make this practical to us? So now we're going to start getting into strengthening mechanisms for metals. Okay. All right, so for metals to plastically deform, dislocations must move. Okay, that is how metals plastically deform. These dislocations move through the material and cause the deformation to occur. And the way we can think about this is we have two people on a seesaw. Let's just imagine that for a minute. We got person A, and then we go through the seesaw, and we have person B up here. Okay. Me and my stick figure drawing prowess here. And then, of course, we have a fulcrum, right? And so we've got two people on a seesaw. Well, one side of the seesaw is dislocation mobility. Okay. How easy is it for these dislocations to move? And we talked about that, the difference between the types of bonding that we have. And let's just say we have one arrow pointing this way and one arrow pointing that way, right? And then on this other side, we have the same thing, but on the upper end of this, we've got strong but brittle materials. Strong but brittle. And then on the bottom, we have weak and ductile materials. Weak or ductile. So, if we want a material to be strong and brittle, we want to find ways to decrease the dislocation mobility through the crystal structures. If we want them to be weak and ductile, because remember, ductility is sometimes something that's highly preferred in metals. Like copper is very ductile, and that is the reason why copper can be made into really, really long strips of wire, right? Very easily, because it's very ductile. It's a very ductile material. It's not very strong, but it's very ductile, right? Whereas we also sometimes want strong and brittle materials, like tool steel, for example. Steel that you use to cut other metals. You want that to be very strong. But it comes with the drawback of brittleness. So when it breaks, it shatters instead of just, bending a little bit, right? So these two things are completely at odds with one another. So if it's ductile, it's not going to be strong. And if it's weak, it's not going to be brittle, which is very interesting. Well, I should take that back. If it's weak, sometimes you can have weak and brittle materials, but not usually of the same kind of material. So, like, you're not going to have a steel that is very weak and very brittle compared to another steel that is strong and brittle. I don't know if that makes sense, but anyway, these are the things that we can tweak, and this is how we tweak them. Okay. So, oh, I'm switching the wrong thing over here. Okay, so how do we do it? How? We're finally getting to the how. So there are three mechanisms. So I'm going to... three mechanisms. To do this. Okay, the first one is grain size reduction. Okay, if we can reduce the size of these grains, we can actually increase how strong and brittle it is. There's something called solid solution strengthening. Okay. remember when I've been talking about alloys, both interstitial alloys and substitutional alloys, and I've been talking about how the alloys are usually stronger than the materials are by themselves. Well, it's because of distortion lattice distortion that is caused by the nature of differing radius atoms being mixed together. Well, that's what this is called. That's solid solution strengthening. So this is where we get bronze. Okay, remember the Bronze Age, where all the weapons in the world were made of bronze because they were the toughest and strongest anybody had. Well, bronze is an alloy of copper and tin, right? And now we know of steel. We talked about the Ulfberht swords. Same idea. Of course, two different kind of mechanisms. Bronze is a substitutional mechanism. Steel is an interstitial mechanism. But they both are solid solution strengthening processes. When we say solid solution, we mean that there is like a solution, like a liquid solution, for example, but it's of solid materials. Okay. And finally, we have something called strain hardening. And we've already discussed this again. Okay. So strain hardening. And it's also like AKA cold working. Okay. Cold working. And you'll remember with this, I was telling you about how if we've got a curve, a stress strain curve, I should say, and we go up to this point and we lay off the load, it will travel back. But now we'll call this sigma y2. And this down here will be sigma y1. Now, sigma y2 is greater than sigma y1, or yield stress 1. And that is essentially what strain hardening is. We are working the material. We are actively stressing it beyond its original shear strain or yield strain. And then we're allowing it, we're relaxing it and allowing basically the material to have a larger yield stress as a result of that, and that's called strain hardening, and that is another way to increase our strength and brittleness. Okay, so we're gonna cut this lesson short because this lesson feeds directly into the next lesson. But I'm going to go ahead and discuss the first of our three systems here, so grain size reduction. But after this slide, I'm going to call this lesson. So strengthening mechanisms for metals, mechanism number 1, we reduce the grain size. So grain boundaries, remember these are our two-dimensional defects, right? When we're talking about types of defects, grain boundaries are 2D defects. Well, these grain boundaries actually act as barriers to dislocation motion, okay? So remember, if we have a slip plane right here, if this dislocation wants to connect into this other grain, it actually has to go through an angle, and it can be very difficult for that to happen, right? Now, if these slip planes are very close to one another, like if it's a low angle slip plane, the grain boundary might not have much of an issue. But as it is, like if it's a very large angle slip plane, difference in slip planes, then this dislocation could have quite a bit of trouble actually getting through. Okay. So at the boundary, the slip planes change direction, and then we have a discontinuity of slip planes. And so if we can find a way to reduce the grain size, we increase the amount of grain boundaries that are present in the material, or you can think of it as the total area of grain boundaries. And this provides more barriers to dislocation motion. This increases our yield strength, tensile strength, and hardness. Okay, makes it stronger and more brittle. And then there's a dependence on we can actually calculate the dependence of our yield stress to the average grain diameter using this equation. And that is our yield stress is equal to some initial stress, okay, some kind of initial material property of stress plus a material constant Ky multiplied by our grain diameter to the power of -1/2, okay? So like if you were ever given a problem on this, you would be given these two constants, or, you'd be given our yield stress and D, and you're asked to find them, right? Okay, and that's it for this lesson. So I will be uploading the next one shortly.